So for a Konvekta 3-row coil, we're showing 4 passes per row. So this is a 12-pass assembly. What does that mean from a energy transfer or energy efficiency standpoint? If you think about the path of flow, that fluid has to flow a lot further through an equivalent Konvekta assembly. So therefore, it's spending a lot more time in a Konvekta coil, more residence time, and more time to exchange energy between the fluid and the airstream. So our approach temps are typically half or less than half of what you'd find with an off-the-shelf type of coil. And then this just shows that same concept. That's what our steel header looks like. You can see the lower right, the fluid inlet is the lower right connection, and then the upper left connection is the return. And then you see 3 drain lines. So because of the way it's circuited, as we saw in that previous slide, because of the way this is circuited, the one thing you do have to remember is in order to fully drain the coil, you've got to open all drain valves that are associated with a coil section. This just shows the exact same concept that we talked about previously. And in terms of thermal efficiency, I think with the off-the-shelf traditional coil, you're less than 50. We're in the range of 70 to 80%, so significantly better efficiency with our coil as a result of the coil design, residence time, in addition to turbulent flow. This just shows a few pictures of our coils on the right. That's our coils installed in an air handling unit, so that's 2 wide by 3 high type configuration. The middle picture is a coil that's come off the assembly line, getting ready to be packaged and then shipped to a destination. And then the left is just another picture of our coil. You can see that the gray header, which is a steel header. It's coated with an epoxy coating. We also, if it's a case where, and we do this pretty regular, consistent basis for coils that go into exhaust air streams that have the potential for corrosive elements. If we're close to salt water, we would apply it to the fins, not only in the exhaust, but the fins and the supply as well. And very little degradation of energy transfer. So it's a pretty thin layer, but we've been using that KO32, what we referred to as a KO32 epoxy coating on the header and the fins for now over 30 years, after having developed it for the pharmaceutical industry to begin with. One other element that's different, Konvekta versus off-the-shelf traditional coils, are the thickness of the fins. So our fins are very rigid. The thickness is 0.4 millimeters, which is 4 to 5 times the thickness of a traditional coil fin, and that lends itself to good transfer between the tube and the fin, or the fluid and the airstream. But in addition, from a maintenance standpoint, our coils are rated to where you can take a pressure washer up to 2600 psi if you need to clean those coil banks for whatever reason. If one reason certainly would be if a filter maintenance lapsed for one reason or another. But we install our coils in exhaust air streams in a lot of instances, and there's a couple applications, one of which is snow melt, which of course the snow melt coils goes upstream of a coil bank. So you're not filtering the air that's coming into the inlet of that coil, but we're able to do that and apply the coils in that fashion, in large part because of the ability to effectively clean those coils if they do get dirty. And then in addition to the coils, which again are designed, constructed in Switzerland, we have pumping skids. So this is an example of a detail that we would develop as a part of the submittal process for a project and for coordination purposes. But you can see some of the different componentry that's a part of a fairly typical skid. This one, if we've got heat exchangers in the list on the right, we've got all systems that we install here. We've got pumps. It's um, 100% redundant inline pump, and our standard is Grundfos. So in addition, any valves that we can incorporate into the fabrication of the skid, we go ahead and do that. And then we send a technician to the factory to do a factory acceptance test, and then they will, they'll test the valves, test the sensors, load the software, and go through a process to make sure that the skid is fully vetted and fully tested before it gets shipped to a mechanical contractor or to a job site. In addition, other standard componentry would include an expansion tank, air dirt separator, and then we've got two electrical cabinets, one of which is a low voltage cabinet where you see the display here. That's a 24 volt DC cabinet. That's our controls componentry goes into that. And then we've got a user interface, of course, that's incorporated into that cabinet. The other cabinet is our high voltage cabinet. So the 460, it's a single point connection. So the pumps from an electrical standpoint are all pre-wired, and all the, it's a single point connection, again, as I said, to that high voltage cabinet. And once the skid gets installed on the site, there's no additional wiring that has to be done other than any of the field componentry that gets installed at the individual air handling units, be it supply or exhaust. The next series of slides speaks to that local user interface. So the local display that's a part of that pumping assembly. And one other point related to the pumping assembly is all the components that are a part of this, there's really nothing that's proprietary to Konvekta other than the software we load into the controller. But all the components that are a part of the skid are purchased here in North America and then, of course, assembled. So when it comes to a lot of federal government programs or requirements, it's typically fairly easy to meet some of the Buy American standards as a result of the fact that all the costs associated with the skids are borne here in North America or in the United States. This is one of the graphics that we develop, and then we'll customize it based on the specific project. But sometimes we refer to this as the Konvekta eye. It's basically a diagnostic utility or a diagnostic graphic. And if you look around the perimeter of that eye, you'll see different system components or system functions identified. And so what this is the intent is to provide the operator, even if somebody is not real familiar with our system or they're new to the building, they can come up to this graphic and pretty easily discern in terms of whether there might be a performance problem or some other issue at play that needs to be addressed. And the way that you can assess that quickly is if you see all the dots in that green section, you can have a pretty high level of confidence that the system is doing what it should be and functioning the way that it was intended or designed. But as performance starts to drift or as operational issues start to come into play, one or multiple of those dots will start drifting into the yellow and into the red. And what we do as a part of the startup process, we have labeling. So we affix a label to the control cabinet. So it'd be in fairly close proximity to this graphic or this screen. What that label has is a 1-800, a toll-free number. So any customer, really anywhere in the world, can call an 800 number, get one of our factory trained technicians on the line on a 24/7, 365 basis. And if we have remote connectivity, that individual can then dial in to the system and help to answer questions or troubleshoot or assist the operator in determining if there is an issue and then trying to resolve whatever the issue might be. This is another graphic. Again, it's fairly typical of what you'd see on any Konvekta system. It's going to vary a little bit. You can see here, this graphic was the first system that I actually installed when I was at University of Denver, but that system consisted of 2 air handling units that are shown on the left by the big green circles. 2 air handling units were down in the basement of the building, and then it was a 3-story facility with 4 exhaust units up on the roof. And so this is just a general overview. As a customer or kind of an operator at the time, this is really the graphic that I focused on to determine, kind of assess or get a feel for how the system was functioning or operating. But this is it's a good example in terms of the type of points that we monitor on any system. And if you look at the different coil banks that are identified here, you can see every coil bank, we monitor the temperature in and out, both on the air side and on the fluid side. And then we also monitor, there's a backnet interface typically between Konvekta Energy Recovery and whoever the BAS contractor is on the specific project. So on the air side, most of those air temps we get through that backnet interface from the BAS system. Most of the points that are associated with the fluid side or the glycol side, we provide. They get installed in the field, including the Belimo valves is our standard. But the valves have feedback in addition. So you can see there's 2 points associated with each valve. One is the commanded position, the other is the feedback. So I think that's just gives you a general sense of what our graphic looks like and what kind of points are a part of each system. The one thing that we've incorporated since this time, so about probably 1.5 years, 2 years ago, we include for every system a flow meter, a fluid flow meter. So you'd see that on a newer system graphic. You'd see the flow rate to each one of the coil banks as a part of this graphic as well. And then every point that was a part of that previous graphic is trended. And then if we have remote connection, we upload the data on a nightly basis. And then that's the information that we use for the optimization that we end up doing over that first year of operation. It's also available via the display to where if the customer wants to go in and look at some of the history or use that trend data for troubleshooting, they certainly have the ability to do that as well. And then the last graphic is just an overview of the system performance. So if anybody, an operator, anybody that's interested in knowing what the performance looks like over a window, any window of time that they choose, they can go to that system display and they can look at a graphic very much like what you see here after having selected a range. So this is from January 1, 2012 to March 10, 2014. So over that period of time, that's almost a little over 2 years, for this system, which is a system at George Mason University, you can see the effectiveness on the right there, 76.6%. So the energy recovery system delivered or supplied 76.6% of the total heating energy requirement. The other 25%, give or take, would have been via heat injection or via the boiler plant. And what each one of those bars represents, the blue bar represents the total heating requirement. The green bar, based on the points that we monitor, we calculate the actual recovered energy. And then the red bar is an indication of what we would expect based on the initial design and the performance guarantee. So we provide a little bit of a window. If you look at that small orange bar, that's a window. So we, as a part of the guarantee, we would expect to fall within somewhere in that window. We allow for 2 to 3% worth of calibration error or drift over that year and subsequent year of operation. In terms of the control componentry that's incorporated into that pumping skid, these are override modules. So every output, be it analog or digital, that's a part of our system, if you open the control cabinet door, you'll see these modules. And as a user or as an operator, you have the ability to go to a hand mode, and you could actually control the system in hand if you needed to or wanted to, utilizing these modules. In addition, these modules are connected to a watchdog circuit. So what we end up doing as a part of the factory acceptance test and or the startup process, we set a default values. So if the PLC were ever to go down, these modules would automatically, we'd lose the 10 volt circuit. And these would go into watchdog, which is represented by that yellow light, and they'd go to a default value. So it would maintain some semblance of control, albeit not optimized control. And then in terms of the initial design of any system, what we end up doing is we look at the weather data for that specific area or climate zone. And then we look at all 8,760 hours over the course of an entire year. And we go ahead and plot or calculate peak demand. And we calculate that peak demand both without energy recovery and then with whatever energy recovery design that we're recommending be implemented for a project. And so what we're showing here is on this graph, the left graph shows the peak demand without any energy recovery system at all for a Roche pharmaceutical facility in Basel, Switzerland. And that peak demand for that specific facility would have been close to 1,200 tons. With the system that we ultimately ended up installing at that facility, we were able to bring the peak demand down to 800, or just below 800 tons. So pretty close to 400 tons worth of peak demand savings. And so again, if you apply that to that International Energy Conservation Code, you have the potential for downsizing your central plant by 400 tons, and so depending on the redundancy requirement, sometimes more than that. But I typically use kind of a rule of thumb calculation, $3,000 a ton. So at 400 tons, that's no small amount of potential capital savings if you're able to size these central plant systems on the basis of these peak demand reductions. And then we do the same thing on the heating side. So this is that Roche pharmaceutical facility as well. The left graph, without energy recovery, the heating demand was about 4,800 MBH. And with the system that we designed for that facility, we were able to bring that down to less than 2,000 MBH. So the peak demand was less than half of what it would have been without energy recovery. And now with some of the new options, one of which I'll talk about towards the end of the presentation, our new option for frost defrost. Normally we design systems to try to avoid any type of frosting of the exhaust coil, but we've got a new design option to where we actively promote frosting, and then we go through a defrost cycle to recover significantly more latent energy from the exhaust airstream. So we see with that design, we can see much more dramatic reductions, and even something north of 50%. We can see something closer to 80 or 90% in certain instances. Now, next we'll get into the different design options. And so I don't know the audience Not everybody may be in a region or climate zone that requires dehumidification. I certainly was not in, in Denver when I resided there. But this is a concept that we've applied up and down the East Coast, certainly. So if there is a dehumidification requirement, what we oftentimes the design includes, or what we recommend, is a design that essentially the supply units are on the left of this diagram and the exhaust on the right. So what we typically recommend is essentially splitting the supply energy recovery coil into two components, and then we install part of the coil downstream of the cooling coil, the other component upstream of the cooling coil. And what we do need is we need about a 6 to 7 degree, an ability to reheat the air 6 to 7 degrees or more when the system's in dehumidification mode. But the economics of this look significantly better than just a traditional runaround with a single coil. So what you see here, this is George Mason University. This is a summer design day, so 90-degree outside air temp, 40% humidity. And what we're able to do is, if you look at this diagram, we've got 74.3 degree glycol in the summer months that we're able to utilize for to generate a 10-degree delta T across our reheat assembly, elevating the temperature of the cooling coil discharge from 55 to 65 degrees. So this design is pretty close to building neutral, but so that's 100% recovered energy. We're not doing any type of additional heat injection here. We elevate the temperature of the air from 55 to 65. In the process of increasing the air temp, we reduce the glycol temp from 74.3 to 61.6, and then we use that 61.6 degree fluid to pre-cool the inlet to the cooling coil. So here we're generating close to a 17-degree delta across our pre-cool energy recovery coil, and certainly significantly reducing, again, that load on the cooling coil. So could be a potential to downsize the cooling coil, and certainly this lends itself to being able to potentially downsize the central plant cooling equipment at the same time. Then here's the heating condition: 0-degree outside air temp at 90% humidity. And the benefit on the heating side is typically this design, we generally have 1 to 2 additional rows of coil in that supply airstream. So if you look at the energy transfer equation, the surface area increases, so we get better efficiency out of this in the heating mode of operation as well. And here at 0-degree outside air temp, we're coming out the fluid temp coming out of that was the pre-cool coil, which is now the preheat coil. We're coming out at 18.6. So this system was designed to avoid frosting of the exhaust coil altogether. And so at 18.6, we know, there's certainly the potential or the chance that we would experience frosting on the exhaust coil. So we utilize a frost bypass assembly, a frost bypass valve that's a part of the pumping skid. We open that to the extent necessary in order to elevate that glycol temp from 18.6 up to 28.4, because at 28.4 we have a very high level of confidence that that temperature is not going to result in any frosting on those exhaust coils. And so we pump the 28.4 to the inlet of the exhaust coils, and then we utilize, in this instance, we had a design basis was 76 degree return exhaust air. So we take the energy out of that exhaust air stream, put it back into the glycol loop, and elevate the glycol temp from 28.4 to 61 degrees. And then we've got a heat exchanger here that's connected to our heating water plant. So we do a little bit more heat injection because that 61 degree temp doesn't quite get us the 55 degree delta T on the air side, on the supply side that we're looking for to hit that 55 degree discharge air set point. So we inject a little bit of additional heat and increase the fluid temp to 64 degrees, which allows us to generate that 55 degree delta on the supply side. And this is what this slide shows is the number of hours above and below specific outside air temperatures. So for any energy recovery system, we really want to maximize the number of beneficial hours of operation. And this is this graph is associated with Philadelphia, Pennsylvania. But I think it's going to apply, something close to this would apply to a big segment of the northeastern US. And if we look at this graph, you can look at that orange bar. So between an outside air temp of 60 and about 75 degrees, that represents over 2,500 hours of operation over the course of a typical year. And so for a traditional off-the-shelf energy recovery system, or an energy recovery system that's not a system that has two coils in the supply air stream, those systems, we would expect them to be off within that region from an outside air temp from 60 to 75. So you're getting zero benefit in that range. In fact, there's a little bit of a detriment in terms of the coils are still there, and so there's still an air pressure drop penalty. With this design that we just covered, we call it the wrap design. With the wrap design, we're seeing significant benefit within that 2,500 hour region, and then enhanced benefit here below 60 because of that additional surface area that we are able to deploy. So we get a little bit better heat efficiency. Oh, go ahead. Yeah.
Yeah, just wanted to make,
Yep.
we have a question, it looks like, from Gaetano.
Oh, yeah, go ahead.
Gaetano, sure. Did you have a question?
Yes, I did. Thank you. My question is how is a freeze condition detected or avoided? What in the software, what is used to detect a freezing condition? So on heat wheels, it's on the leaving air condition, on the exhaust side. If the RH gets too high, then the wheel is slowed down. I was just wondering what logic is used in this case.
Yeah, no, that's a good question. And so we monitor, temperature in and out of each one of the exhaust coils, both fluid temperature in and out and air temperature in and out. And we know based on experience that 28.4 degree temperature coming in is not going to lend itself to frosting. But what we typically do, and our typical recommendation, is that we monitor on the exhaust air stream not only the temperature but also the humidity. So in this case, if in reality, and this is a design document, but if in reality the incoming humidity is 10%, we end up resetting that temperature down, because we can if we can reset this 28.4 degree temperature a little bit lower, we're going to get better recovery from the exhaust coil. So, oftentimes, and our typical recommendation would be to monitor not only the air temp coming into the coil, but also humidity coming into the coil.
Right, but what variable determines whether the frost condition is oncoming? Is it the properties leaving the exhaust coil? Is it the relative humidity leaving the exhaust coil, or?
No, we know it's really the temperature coming in is the driving factor. But again, it's this temperature. That's what we monitor very closely. But again, we do, if we have humidity and we've got an accurate humidity indication for the entering exhaust air, we'll go ahead and reset that to to some extent in order to boost or enhance our recovery.
Okay, thank you.
But it's really the temperature coming in, yeah, that kind of dictates.
Thank you.
So yeah, yep, yeah. Thanks for the question. Here, this is another design option. So this is actually the option that I ended up deploying at the two projects at University of Denver, and we've applied it, a lot of different instances, including down in Phoenix, Arizona. But what we're showing here is, of course, a supply air handling unit and a energy recovery coil on the left, an exhaust air handling unit on the right here with its associated coil, and then upstream of that exhaust coil, we've got a evaporative cooling element. So it can be, some form of adiabatic. Really, any type of evaporative cooling product would work. But what we do here is, what we're doing here, if you look at this design condition, and this is Atlanta, Georgia. So, it works really well in airy climates because you've got low humidity coming into the exhaust, typically low humidity entering the exhaust air stream. But it can also work in humid climates if you're doing dehumidification. So this is kind of an alternative maybe to a wrap design in those kind of climates. But here we've got a summer design condition, 95 degrees, 50% relative humidity. And at that design condition, we're coming out of the supply coil at a fluid temp of 88.6. So rather than try to reject heat from that 88.6 degree fluid into a 75 degree airstream, we use that evaporative cooling process and we drop from 75 to 60.5 degrees. And then we can much more effectively reject heat into that 60 degree airstream. What I was seeing in Denver in a low humidity, arid climate, we were getting down into the low 50s for the two projects that we installed there. But here we're able to get to 60.5. That nets us about a 20 degree delta, fluid delta T. So then we come out of the exhaust coil at 68.3, and then we pump that to the inlet of the pre-cool coil, which nets us something pretty close to a air delta T of nearly 20 degrees, just under 20 degrees. So this is something, that can work really well, especially in cooling dominant climates or climates that have a pretty significant cooling requirement in general. And the one element, you're introducing water into an air handling unit. So I'm always a little bit cautious with respect to a recommendation for this option. If the end user or the customer, the operator, isn't familiar with whatever type of maybe adiabatic evaporative system is being recommended or suggested. And here's a couple other design options. So this is what we call our free cooling option, and it's a pretty simple, not a real expensive venture typically. And what this includes is a three-way valve. You see on the bottom left of the slide, a three-way valve, a heat exchanger, the red box, and then a pump. And so this was it was a project in Milwaukee, in the Milwaukee, Wisconsin area. And they had internal cooling requirements, even if it's a minus 20 degree day, which I think minus 20 was the design point there. On a minus 20 degree day, they still needed to cool some internal areas, including there were electrical closets and server rooms internal to the building. So what we ended up suggesting was a free cooling option. And so certainly, at minus 20 degrees, we're coming out of that preheat at a really, really low, we're going to come out at a low temperature. It might be something less than 10 degrees. So we've got all kinds of cooling capacity at minus 20. But what they asked us to do is they said, we want to know up to what's the highest outside air temp that we can go to and still generate 35 tons worth of cooling to support those internal loads, because we want to keep from running our central plant systems to the extent possible. We don't want to run those systems at really low load or low outside air ambient conditions. So this analysis we showed, and they did, custom design on the internal fan coil units that supported those areas to where we're operating based on a chill water supply temp of 57 with a return of 67 degrees. But what we showed here at 50-degree outside air temp, we were able to deliver that, that 35 ton requirement here. And in doing so, we're coming out here at 50, we're coming out at 53.7 degree fluid. It's the blended temperature is 54.2. So we're using 54.2 degree fluid to generate those 35 tons worth of cooling. And then we're seeing the glycol loop elevate because that heat gets rejected into the glycol loop. We're seeing the glycol loop elevate from 54.2 to 56.4. That's a part of that process. When we get into the extreme outside air conditions, it's a benefit because it reduces the amount of, at minus 20, it's reducing the amount of bypass energy that we're bypassing. So we can put more energy, if we reject heat from those internal loads, we can put more energy into the supply coils as a result of that without having to bypass that energy. And then this is probably one of our newer designs. This is a project that we're doing a final startup. It's a Boston project, and the goal here was to try to really, it's kind of an electrification concept. And so what we see here in the Boston climate, this is showing, we're doing a snapshot at 20 degree outside air temp. And this combines two different concepts, a heat pump that's basically connected directly connected more or less. We've got some heat exchangers, but that's connected to the glycol energy recovery loop in parallel to our exhaust coils. And then we also have the frost defrost, and I'll talk about that a little bit more when we get to the next slide, but it's got the frost defrost concept in play. And so here, if you look at 20 degree outside air temp, we're coming out of, and this is the wrap concept in addition to a third supply air coil, which is the snow melt coil. So that leftmost coil is actually upstream of the filter bank and used primarily for snow melt. But at 20 degree outside air temp, we're coming out of that snow melt or the supply air handling units at a fluid temp of 30.5. So normally that's above the 28.4 degree kind of critical temperature that I'd mentioned. So certainly no need to open the frost bypass valve at all. And normally in a conventional or typical system, we would just go ahead and pump that directly to the exhaust coil. But here, because of that frost defrost sequence, we utilize a heat pump. So we extract some energy from the glycol loop with the heat pump. And in the process, we drop the fluid temp from 30.5 to 22.6, which is well below 28.4. And with 30% relative humidity, we certainly would expect to see frosting occur at this condition on that exhaust coil. And what that does, we lower the fluid temp to 22.6. So in order to maximize recovered energy, we want to expand the delta T between the incoming fluid and the incoming air temp. So here, we've got what is that delta T? 30, 40, 50, 48. about 48 degree delta T that we've been able to generate. And with frost defrost, we were able to extract, because we're going from basically an airstream, and you're going from gas to liquid to frost. So you're going through two phase transitions. And what that allows us to do is increase our net recovered energy. And in this case, in comparison to a traditional energy recovery without the frost defrost, we're 13.4% above where we would be if this were just a conventional design. And what that allows us to do, that additional 13.4% allows us to generate a fluid delta T across that coil of 37.5. So we go from 22.6 to 60.1 degrees. And then on the other side of the heat pump, on the condenser side, we go ahead and, the energy that we've extracted here, we re-inject along with some additional energy via the compressor. So the heat pump takes us then from 60.1 to 71.2, which is exactly what we need to generate that 40 degree delta and hit. This was the discharge air set point in this application in a heating mode was 60 degrees. So at 20 degrees, in Boston, we can go all the way down to 20 degrees with zero input from a gas-fired boiler plant with this combined heat pump concept. And then we've got some different iterations of this concept as well, to where we could go down to zero, or in some instances, I think less than zero now, with a heat pump applied in a slightly different in a slightly different way, in a way that we have a sample. We've got a system installed that's up and operating at our plant or our factory in Basel, Switzerland, or I'm sorry, St. Gallen, Switzerland. So the concept, I talked about frost defrost, and you can see here we establish zones. So for frost defrost, those systems are going to tend to be larger in size, and we need about 6 to 8 exhaust zones to be able to effectively go through a rotation, a defrost rotation. And what the concept itself is very simple. We allow the coil to frost, and we monitor. We know the coil characteristics, so we're monitoring fluid in and out and air in and out. So once we get to a point where we're seeing about a 10 to 15% increase in the air pressure drop as a result of the frosting, we would go into a defrost mode. And what the defrost mode is, there's a valve associated with each one of those zones. We simply close the valve and allow the return air to defrost. So we're not putting that in the last example. We're not pumping any longer. We're not pumping the 20 degree fluid through the coil. And what we found is the defrost process takes about 1/8 to 1/10 the time that it takes to frost it. So, our software, we establish the timing mechanism, and then we just start defrosting on a rotational basis. And then, we also go with our standard design would be 8 fins per inch. So we space the fins out. We go to 6 fins per inch. That's the standard for this concept. And, the coil design, we always go with the epoxy coating if it's a frost defrost application. In terms of support in general, I talked about that toll-free, 24/7 toll-free line. There's a variety of other support elements that we provide, including we've got a spare parts inventory at a facility outside of Atlanta, Georgia, that we can ship typically next day air to any place in in the country. And then we've got some extended service options as well, be it quarterly. Typically, it would be an annual inspection by a factory trained service technician would come on site. And then as a part of that, we go ahead and extend the monitoring beyond that first year that's included in a standard contract. System redundancy. A lot of times, questions related to system redundancy come up. The question if, what if the PLC goes down, things of that nature. But we design a redundancy and resiliency into the system. From a mechanical standpoint, we've got 100% redundancy on the pumping side. In addition, the heat exchangers are typically selected at N+1. In particular on the heating side, not always on the cooling side, but we can certainly do N+1 on the cooling applications as well. We've got the manual override modules. So if a user ever were to want to control the system in a manual mode, certainly you have the ability to do that. And those modules, again, have default settings. So if the PLC were to ever go down, and it's an industrial type controller, so we rarely, if ever, see that happen. But if that goes down, we lose the watchdog circuit, or the watchdog voltage. It automatically goes to a default mode of operation. And then we also provide a spare flash card with the software programming. So if something happens to the operating flash card, you've got a backup. You can plug that in and cycle power, plug it in, start up again, and you should be off and running. And then we provide UPS on a lot of systems, in particular if we're providing primary heating functionality. So if we have heat injection to where our coil is providing 100% of the energy recovery and 100% of the heating functionality, then we always include a UPS to make sure that we can maintain power if we get a power bump. And a lot of that has to do with, we want to make sure that we keep a stable communication with the BAS via that BACnet interface. Here is some of the recommended maintenance intervals. Really pretty straightforward in general. Two primary components, the coils, and that's really just a matter of keeping the coils reasonably clean or doing your filter maintenance. We recommend the customer inspect on a quarterly basis, and then if we're a part of some sort of service agreement, certainly our technicians would do inspection of the coils as well. And then the pumps are the other major component. Again, they're Grundfos, so not a lot that you have to do there. Typically, you grease the motors based on it's a lead lag operation. So a typical system, based on what we normally would expect to see runtime wise, you'd be greasing those once a year. And then Grundfos recommends replacement of the motor bearings essentially every 5 years. There's a couple other items that are included on the skid. That the Beckhoff, the flash card, we recommend replacing that every typically 2 to 3 years. We would do that as a part of a service agreement as well. Expansion tank, test the bladder pressure. So test the bladder pressure to make sure the bladder itself is still, the integrity of the bladder is still good. The Kunkel, we use Kunkel pressure safeties. So we've got a high and low, 125 and a 225 PSI. Kunkel's factory recommendation is to replace those every 5 years. What I usually recommend is to maintenance personnel that if they've got a maintenance program already in place, kind of apply those standards to the components that are part of our system as well. And then the air dirt separator, just a matter of blowing that down initially. It's a closed system, so once you see evidence that there's no particulate coming out, inspect that once a year from that point forward. And here's just kind of a rundown of what some of the items that would be a part of an inspection that one of our service technicians would do on site. And so a lot of facilities, the more common interval would be the annual. So we do everything that was on this monthly, quarterly, just some very conventional checks, looking at system pressure, making sure the valves stroke open and close, testing the lead lag pumping functionality. And so we do all those in addition to what's on this list as a part of an annual inspection. And here's where we would replace the controller, the flash card, if the system's under some sort of service agreement. We do periodically get asked for a recommendation in terms of spare parts, and this is typical. This would be a typical recommendation. So some customers, if it's mission critical, would want to put some subset or all these components on the shelf at the facility. But again, these are items that we typically stock at that facility outside of Atlanta, Georgia, that we can ship next day air if there's a need for that. And then, as I had mentioned earlier, every system that we install includes a performance guarantee if we have remote access to the system. And typically, and that's generally via VPN connection that's authorized by the local IT facility. But if we have that remote connection, again, we upload the data on a daily basis, and then we use that as a part of the optimization process. This is just the formula that we apply. So it's a pretty simple formula. We apply it at different operating points. So this is a 32-degree outside air operating point, and so we would plot a number of operating points. We can provide that up front so that an owner engineer knows what the performance should look like. And again, we've got the energy and financial assessment, which is kind of a spreadsheet that gives you an overview of what kind of energy savings that you should see. And then if for some reason we don't meet that guarantee, what our contract says is that we pay the difference in the owner's excess energy bill for that year of operation and/or multiple years, depending on how the contract is initially set up or configured. This is that International Energy Conservation Code that I'd referred to before. So this is the actual terminology. And so if you look at the wording, the red, heating and cooling loads shall be adjusted to account for load reductions that are achieved with energy recovery systems utilized in the HVAC system. So if this is applied verbatim by an owner engineer, that's when we can take pretty significant advantage of downsizing if we can take those savings and roll them into the financial assessment or financial calculations. The payback of our system, a lot of times, we see 5 years or less if we have the ability to do that. In some instances, we've seen systems that were cash neutral from day one. So they were able to purchase our enhanced energy recovery system with no real pricing penalty at all, or no incremental pricing penalty at all. And then I mentioned, we try to, or if at all possible, we want to get involved as early as possible in the design process. So this is a list of all the different elements that an energy recovery system can touch or can have an effect or can have a benefit with respect to. So I just put this list together, and I try to keep a lot of these items in mind if we get involved early, and if there's specific issues or concerns or problems, like for instance, the bottom left, replacement of underground chill water steam piping. So in a campus environment, if, say, as an example, they're looking to add 15,000 square feet of space and then the mechanical equipment to support that additional square footage. If you can apply energy recovery to that equation, a lot of times, where you might have to upgrade underground chill water steam piping, you can avoid that altogether based on an ability to reduce peak heating and cooling demand. So, in those instances, if it's a ground source heat pump project, so if you look at the ground source heat pump and you look at the cost of ground source, if you can take into account our peak demand savings in sizing a ground source system, just those savings will pay, usually those are a lot of times double or more than double what our system costs. So that's a pretty easy decision, to go down the design path with Konvekta. And then net zero, certainly if there's net zero, any type of sustainability initiatives, lead goals or lead points that are needed, we can oftentimes assist with those elements as well. And then this just summarizes the benefits that I think I mentioned kind of throughout the presentation, but higher annual efficiency. So a lot of times, depending on what options are applied, but from a heating standpoint, it's not uncommon to see system designs that deliver 90+% of the total annual energy requirement or heating requirement. So then you only have 10% 10% that has to be made up through central plant inputs. Peak load reductions, we talked about that multiple times. Performance guarantee, the variety of options available depending on climate zone and specific goals. Easy to use and maintain. You can clean the coils up to 2,600 psi and then the toll-free number. So that's really everything I had. I think we're pretty close to the window that I was thinking. So I don't know if there's any questions, any additional questions, or if there's other material. If you have any questions, maybe related to other options that we have on the table, or I'm happy to answer whatever the questions are out there.
Folks, if you have a question, you can go ahead and raise your hand with the button on your screen if you're using your computer or your phone, or you could just shout it out.
I do have a question. It's quite simple. Will these slides and the recording of this meeting, will it be made available, or can it be made available?
Yeah.
Correct.
Yeah. I can get this to you, David, and if you want to distribute as you see fit.
Yep, absolutely. Gaetano, if you want to email me after, you can go ahead and do that, and I'll send this to you.
And we would email you for the PE certificate as well, I guess?
Correct. Yep. Okay. So anybody who's still on here, we typically issue those within about 30 days of the course. If it's a larger class, this is a smaller one of our classes, so it shouldn't take very long. But we typically issue those within 30 days, and you should get them directly to your email.
Thank you.
All right. Any other questions? All right, Tom. Really appreciate you doing this for us, and everyone, we hope to see you again next time. Thanks again for joining.
Okay. All right. Yeah.
Thank
Thanks
you.
a lot. Okay.
Thank you.
Have a good day. Bye.